Hey, thanks for your patience, Stet.
No
So
problem.
once you bring up your slides, I'm going to read your intro. The Stet Sanborn is presenting cold climate commercial electric construction. So Stet is an award-winning designer with a background in both engineering and architecture. Stet Sanborn serves as the engineering discipline leader in SmithGroup's San Francisco office. He specializes in net zero energy and net zero carbon design. He is a leading voice in statewide decarbonization efforts, this is true, and building electrification, recently supporting the city of Berkeley, San Jose, San Francisco on their electrification ordinance development. He also currently sits on the San Francisco Mayor's Building Decarbonization Task Force for New Construction. Welcome, Stet.
Thank you.
Thank you for presenting on cold climate commercial decarbonization. It's
yeah, no problem.
So excited to check it out.
Okay. Well, I have way too many slides, so I'm going to jump in because this is obviously a topic that I get a little excited about.
Well, and lunch follows, so you can go a little bit into it. It's okay. Yeah, like take your time. You can have a whole hour basically if you want. It's okay.
Oh, perfect. Well, it definitely builds off of what Kip was talking about as we try to take some of the lessons learned. I mean, something that we're doing within SmithGroup is trying to take a lot of the lessons learned that we've gotten from California, from field demonstrations, from product testing, and see what and how to translate which ideas to our other climate zones that we work with. And there's a big need. It's not just a coastal thing. We want to decarbonize everywhere. And a lot of folks also forget that California actually also has cold climates. If you just drive up the road from here to Truckee, you're in California climate zone 16, so it's a cold climate. And so trying to find which technologies pair with which locations is really important so that we don't, I think the biggest threat to our efforts on electrification and decarb is over-promising performance and ignoring the design decisions that need to happen when we're actually applying appropriate technology for beneficial electrification. We were just talking about the ISO. So here's the ISO for California, and a ton of renewables. We're doing great. Pat ourselves on the back. It's amazing. Decarb. We're doing really fun work. A lot of what we're doing is trying to figure out, like, is it a benefit in other climate zones? And so I've got a project right now in Chicago that we're trying to decarbonize a high rise. It's extremely challenging, not for multiple reasons. One, their ISO, they're actually served off of an East Coast or sort of mid-Atlantic, or not mid-Atlantic, Northern East ISO, just for the little Chicago for ComEd. And they still have significant amounts of coal power on their grid. To offset that, though, they have a ton of nuclear as well. And so from a carbon standpoint, it's kind of a mixed bag. But their profile is quite different, and their temperature profile is quite different. And so it changes how we approach electrification, as well as what sort of coefficients of performance that we need to be able to attain to hit our decarbonizing goals without increasing utility bills. So we all know in California, we've been getting rid of furnaces, getting rid of sort of units and closets, and going to mini splits, as Kip mentioned. VRF, you see a ton of that now on the market. It's not my favorite system. There's so much refrigerant that we're pumping around that the losses are going to outweigh the benefits. But regardless, it's a technology out there that is enabling electrification. My personal favorite is moving towards really high efficiency air to water heat pumps. Now they have to be designed appropriately so they don't, you don't kill your compressors. But there's a lot of technology out there that is enabling that lets us still do hydronic distribution, which is still my favorite. And it warms my heart when I hear other people who get excited about hydronic distribution. It might be old school, but it's zero global warming potential on the distribution side. And then a ton of work, and Sean's been involved with this, Ecotope's been involved with this, sort of driving this push towards heat pump water heating, whether it's the residential scale or the commercial scale. There's way more options even this year than there were like 3 years ago even on the market. So it's rapidly changing, and it's really exciting. And I would say that California right now is ahead. California, Seattle, sort of Oregon are ahead of most of the country in discovering the challenges, whether it's on the true performance of the systems, whether it's defrost issues when we're on our sort of coastal cooler temperatures while simultaneously having a really high wet bulb temperature. And so those challenges we're trying to translate over to colder climates to make sure that they don't hit the same ones, so that we don't lose momentum, and that's really important. And then the last sort of introduction sort of piece that I want to share is there's rapid movement, right? Well, it's not as rapid as we need it to be, but it is changing faster than HVAC has changed in a long time. But a movement towards these new class of refrigerants. So we're all used to 410A and 134A. Those I would say are now very quickly going to become legacy refrigerants as we try to move down to lower GWP refrigerant-based refrigeration cycles. So right now, a lot of folks are moving into R513, especially on the domestic hot water side. We can make hotter water with R513. But R32 is a readily drop-inable, if you will, replacement for 410A. And so with half the GWP, it's sort of a stepping stone, I would say, towards getting towards our ultimate goals of getting down to natural refrigerants with a GWP of 1 or 0. So just as an example, we have a project that we're working on here locally using actually the exact same technology that we're looking at in another climate zone. So I'm just using it as an example of a 200 unit apartment building. When we start to look at which systems pair with which use profiles, I hear a lot when I'm on calls in California that they're like, oh, heat pumps, it has a COP of 3, it's great, saves the day. And yes, a heat pump can have a COP of 3, but oftentimes they don't. And especially when we look at air source heat pumps, that COP is highly variable, and it tends to drop off at the exact same time that we want it the most to be high. So here, if I was just running a quick calc on, what's it going to cost my client to make hot water for this project, 200 unit apartment, it's about $100, $120 a day if they're using fossil gas. If I have a COP of 3, annually averaged out on a heat pump, I can reduce the operating cost of the system. It's when I promise a COP of 3 and deliver a COP of 2 during the winter that cost parity drops off quite a bit. And it becomes far more apparent when we move outside of California's utility cost regime. So in the Bay Area, if I can hit a COP of 2.7, this is sort of the local Bay Area looking at PG&E rates for this size project. If I can hit a COP of 2.7, I'm on cost parity with a fossil boiler. So I can win the day if I design a system that can readily achieve a 2.7 or better. If I move that same project to Chicago based on their utility rates, I actually need to get quite a bit higher. I need to hit 3.06 before I even break even on an operating cost standpoint. If I go to Denver, it gets even worse. So colder climate and their utility rates heavily bias gas, even more so than California. And so now I need to get to a COP of 3.4 during the full range of operating, average out to 3.4 in order to hit cost parity. And that's really important because COP is driven by my design conditions. And when I move to cold climates, those design conditions get far more challenging than sort of, Central Valley, California, or especially coastal California. So I go to these cold climates and we're like, rah, 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 DRF, air source heat pumps, they're our friends. But when you start to look at the performance curves for most air source refrigeration equipment, you're going to start to see a trend, and it gets pretty severe. It's both dependent on what temperature water I'm trying to make for the building, but it's also heavily dependent on outside air temperature. So you can see as I move towards the left, I get colder and colder. The COP of the system, and this is just the core, the heat pump itself, is dropping off significantly. If I go past 40 degrees, even lower, like Kip mentioned, we're going to see COPs that are approaching 1. Not just the COPs, the coefficient of performance of the system, but on the graph on the right, you can also see the actual heating capacity of that system drops as well. The system has a limited capacity from the compressor, the size of the heat exchangers, to extract a certain amount of heat. And as that delta T across the heat exchanger from the outside air temperature drops, that temperature, that capacity of the unit is going to drop as well. And so these are the two things that we're fighting when we try to translate our electrification strategies to colder climates. There's two things that are sort of in the marketplace that help us. One, as Kip mentioned, are multi-speed or inverter-driven compressors that can actually do better load matching in the operation phase. And you can see from the graph on the left, this is sort of true COP actually delivered on a project as the outside average daily temperature is dropping as you go to the left. And you can see those, even with an inverter-driven compressor, it still is not hovering at 3. What everybody's using for their carbon intensity conversions, oh, it's a COP of 3, it's great, every hour of the day is wonderful. That's not true. And so the COP is dropping off, but inverter controls will allow you to at least bump that back up and hold it relatively steady down until when you get to the 0 degree Fahrenheit mark. After that, it's pretty much an electric resistance heater. On the right, though, is technology that's starting to infiltrate the market right now within the refrigeration market, and that is looking at what's called enhanced vapor injection. And I don't know if you can see my mouse, but the key thing is in the lower right-hand corner, just past the condenser heat exchanger, is an extra valve. There's an extra solenoid valve that's actually going to peel off a little bit of that refrigerant, run it past its own expansion valve, and steal additional heat off of the main refrigeration loop. That allows us to subcool the refrigerant that's going to the outdoor unit, or is in the outside half of if it's a monoblock style system. That increases your delta T on the heat exchanger and is going to allow you to pull more heat out of very low or sub-freezing outside air temperatures. The super cold refrigerant goes back to the compressor and then is blended with the warmer refrigerant that was peeled off earlier. So there are strategies to do sort of multi-loop refrigeration cycles or paired refrigeration cycles to get better delta T's across your heat exchanger. And those technologies are critical for cold climate applications. So sub-freezing, sub-0 degrees when we're going down into the negatives, which is, to be honest, this week in Chicago, I talked to my brother, the high was like on Monday was like 2, like Fahrenheit. And my parents are in rural Iowa. They've been below 0 for the whole last week. And so when I talk to them about electrification, they're not excited because of that low outside air temperature and the technology not being matched well for it. So where do we go when the outside air temperature isn't that good? Well, we're super excited about looking at every other source on a building that we can get good quality energy. So in the case of domestic hot water production, I love to look for the sewer. How close is the sewer? How much volume can I store on site so I can extract the heat out of it before the effluent leaves the building? So we're heavily involved with applications of using both the Shark and the Piranha from Shark Energy, of using those for domestic hot water production in very large scale facilities. And a big reason for that is the effluent leaving the building is at an extremely consistent temperature. If you think about it, when I need hot water in a residential building, it's likely because I'm using a lot of showering, shower water. Well, that wastewater coming out of the shower is a great source to steal heat from. And so instead of trying to steal heat from 0 degree temperature outside, I can steal it from a 70 degree, 75 degree interior or effluent temperature leaving the building. So instead of a COP of 1, I can hover around a 4, 4.2. That difference is huge. And as I mentioned earlier, when we look at cold climates, if I need a COP of 3, 3.4 year round to show cost parity against fossil gas, then I need to find sources that have a better COP. And so in this case, it's essentially a water source heat pump, the heat exchanger off of the wastewater stream. Now that's not just for domestic hot water. This is a project that I share quite a bit. This is the DC water headquarters in Washington, DC. In this case, it's a building level system where we're doing all of our heat exchange with wastewater. It's a pressurized wastewater line that runs adjacent to the site. We're using heat recovery chillers and a wastewater Shark heat exchange to do all the space heating and cooling for this building. So in the summertime, that sewer water is cooler than outside air temperature. In the wintertime, that sewer water is warmer than outside air temperatures. So I get really high COPs year round. But a key strategy is before we start looking for all these other places to go get energy is trying to find ways that we can recover our own waste heat. So whether that's the sewer water leaving my building or my own rejected heat that normally would go to a cooling tower. Finding that middle band of heat recovery is actually the highest place that we can put our efficiency dollars because our COP is going to be between 6 and 9 when we're doing full heat recovery, and we don't really care what's going on outside of the building. So we're moving a bunch of projects in like retrofits, new construction of going towards all electric or what we call semi-all electric. And that's even including large central plants that are serving entire campuses. And so some of those campuses we're transitioning off of steam. And believe me, if you want to think about pushback in the Bay Area or in California for electrification, go talk to a steam plant engineer at a plant in Michigan, and I'll tell you about pushback. But we're still doing it. We're showing that it can be done, and there's a pathway to do it. But sometimes it does require still having some natural gas component for some worst case uses, like steam generation for sterilization, for instance. But we're working on that one. We've got some projects that we're trying to go to steam generating heat pumps. So one of the big things that we do in cold climates, as I mentioned, is look for other places to store or pull heat out of. And a really great one from a market standpoint in the Midwest, upper Midwest, is geothermal or geo-exchange. And that is because drilling costs there are very low compared to out here. And we can just beat the pants off of the COP or coefficient of performance when we do that based on any fossil gas system. A key to doing those really low entropy systems is actually the design temperature of what we're trying to deliver to the space. So classic cold climate is to take a 2000 degree flame, make 250 degree steam, run that through a heat exchanger to make 180 degree water, run that through a building and deliver 85 degree air to a room so that I can make a room 75. It's insane. Like, we're making something extremely hot just so that we can make something neutral, relatively neutral. And so one of the biggest things that we do on the design side is reimagine the regime for temperature distribution. When we go to hydronic distributions, like with chilled beams, chilled boxes, we can go to 95 degree delivered water, with a 20 degree delta T between the space temperature that we're trying to get to and the temperature of the water that we're delivering. I will say that this gets even more beneficial when you look at expanded thermal comfort, mixed mode components with natural ventilation. We have way more flexibility with these temperatures, but making stuff really hot just to get back to neutral is insane. And heat pumps aren't going to do it. But we can certainly make very efficient heat pump systems that are delivering 95 degree water. I can give you a COP of 4 if I'm making 95 degree water. So whenever we're doing these really large scale master plans or retrofits, our first task is actually looking for waste. It's the first thing that we do when we're doing big utility scale master planning is I'm finding all the places that they usually dumping heat. Cooling towers running in the winter. Are you insane? In a cold climate? I want that heat. I need that heat. One of the big things that I hear all the time is, oh, we need to put all of our data centers in the Arctic so they can passively cool. That's insane. I want your data center next to my multifamily project. Do you know how much hot water, domestic hot water, I can make off of a data center? Nobody would have to worry about hot showers. It would be amazing. So finding all these waste sources and co-locating them or connecting them by a distributed energy system so that we can take advantage of that is really, really critical. So this is a simultaneous heating and cooling graph for an entire campus in Michigan. So Michigan, everyone's like, it's so cold. Oh, how can you heat them? When we actually start to take advantage of that simultaneous heating and cooling and stealing the heat out of our waste streams, so out of the exhaust streams, the ventilation hoods in labs, chemistry labs, when we start to steal that heat back, it actually covers a good chunk of our heating load to the point where almost all of our heat across the year is simultaneous heating and cooling. And even in cold climates, we can actually see that we can turn it into, from a central plant standpoint, a cooling dominated climate. So all of a sudden, I'm less worried about that COP down at 0 degrees because I can actually find some smaller equipment that could pick up that load. So this is an example in Michigan, Oakland University. It's a VRF system, so forgive me, but it is a water-cooled VRF. So instead of trying to look for outside air temperatures that are warm in a place that they were never warm, we're using ground-coupled, so geothermal tied with VRF for pretty low-cost installation and extremely high performance. The nice thing about GeoExchange in cold climates is that it's very expandable. So you can start a geo field that matches one building load and slowly expand it over time to start picking up multiple buildings. And as you add each building on, you get more load diversity across the whole set of buildings, and you can actually reduce the total installed cost of the system. So you can deliver a decarbonized project in the Midwest or upper Midwest, cold climates, and you can do it extremely cost effectively. I wanted to give one sort of case study locally, which we're using the same process. So this is actually San Francisco. I've been helping the Unitarian Universalist Society of San Francisco decarbonize their 1906 sanctuary and 1960s center probably for the last 12 years, doing incremental decarb projects across for them, including adding PVs and weatherization and all sorts of stuff. This is their existing electrical use over the last year. So this was 2020 data or 2021 data. You can see the beautiful blue part in the middle where their PVs are actually overproducing and they're exporting power. You can see the part where the blue stops where somebody flipped their inverter or their panel off because it's accessible outside. And in San Francisco, that's a fun thing to mess with. But what I wanted to show you is what we actually did on trying to get them off of natural gas or fossil gas. So this is taking their gas usage data, applying it through a temperature-corrected COP curve, and estimating if we were able to get them onto a heat pump, what their gas usage would, or what their effective electrical add would be. So if you aren't familiar with graphs like these, it goes from January on the left to December on the right, and it goes from 6 a.m. or midnight a.m. on the bottom, it goes up to midnight at the top. What you start to see is both the periodic nature of their facility, these weekly bursts as they open up their sanctuary and try to warm the whole facility up. But you also very quickly can see some of the peaks on the lower left, these red spots. These are the spots that are the cold time of the year, morning warm up, and that represents their peak load. And a lot of folks, when they're looking at buildings, are designing around peaks. And when we're doing that with air source heat pumps, you need to be very careful because you will radically oversize a system if you design an air source heat pump system designed around that hour. I don't need that much power, that much heat for that long. I just need it for a brief window. And so what we are very strongly recommending to folks is that when they're doing their design considerations, they're looking at the duration that peak occurs. And we are highly encouraging folks to include thermal energy storage as a means to shave that peak. You don't have to do batteries. If you want to compare pound for pound or dollar for dollar, thermal energy storage is still a sexy technology that is super dumb, but it's extremely easy to maintain. It's extremely benign environmentally, and it can drastically reduce the number of heat pumps that I need to install if I can shave those peaks. So in this case, we're looking at a new R513 machine that can make 160-degree water all the way down to 5 degrees or so. But we don't have to install 2 of them because we're able to shave those peaks and we're understanding the load profile of the building that we're actually designing. And that is important because space is always an issue. When we start looking at footprints for all this equipment, air source heat pumps take up way more space than their fossil gas counterpart. And so we need to be smart about the sizing of these systems, right sizing them, and making sure that we can find a place for them to sit, especially in the retrofit situations. As I mentioned earlier, we're on this constant drive down to get to natural refrigerants, ammonia, CO2, et cetera. And one of the most exciting things that's just now getting onto the market and is actually available are commercial grade CO2 heat pumps. If any of you guys have done CO2 heat pumps in the past, they're typically targeted at domestic hot water systems because they need such a high lift. They want to take cold water and make it really hot. And in field studies where folks have tried to do combo systems, they've really struggled on the space heating side because we don't see those delta T's on the big delta T on the water loop for space heating. So we've been working on an application of taking CO2 heat pumps, and this is sort of a very crude diagram of being able to take a high lift CO2 heat pump and pair it with that low entropy design system that I talked about earlier, where instead of delivering 180-degree water to the building, we get them down to, say, 120. If I can deliver at 120-degree water, I can certainly get a 30-degree delta T or more on the hot water loop. But the key is to not use a heat exchanger. So not a domestic hot water system trying to be a space heating system. The key is blending down that 190-degree water with my return water loops. I'm just injecting the hot water to get it back up to 120. But that lets my tank continue to stratify. It allows me to store water at a very high temperature and a very compact footprint. But it gives me tons of flexibility in load shifting, drawing out my heat pump production time, so I don't need as big of a heat pump. I'm going to scream from the rafters as much as I can, but I know batteries are sexy. I love batteries. We're doing a bunch of microgrid projects with PVs and batteries and islanding. Thermal energy storage for large commercial projects and even mid-sized commercial projects is still incredibly sexy and gives me way more flexibility for load control when I'm pairing it with a heat pump appropriately. So in this particular system, this is an air source heat pump, CO2 refrigerant. It also has a secondary heat exchanger that allows me to do free heat recovery off of a chilled water return line. So I can get simultaneous heating and cooling from this device. I can push that COP of 2.5, 3, up to 6, 6.5. That is how we cost effectively electrify in cold climates. The beauty of a CO2 heat pump is because it's a transcritical CO2 heat pump, it's way up there in the transcritical zone. It's making very hot water at very low outside air temperatures if I'm in air source mode. And so it's a great technology that I can't wait to see deployed in cold climates, paired with thermal energy storage. Because what if I don't have to make hot water at the worst day condition when it's 0 degrees outside? What if I can wait 4 hours until it's 10 degrees outside or 15 degrees outside? My COP goes up, my capacity goes up, and I've got the storage there waiting to accept it. So my big shoot it from the fireworks is don't forget about thermal energy storage. It's really important. But here are my sort of top 5, if I'm sort of walking away, my top 5 things to share with you. First one is you have to look for heat recovery. In cold climate designs, your waste heat is your friend. It should be your source heat. Waste heat and source heat should be the same thing. You have to actually design your system. You cannot throw a heat pump in and read the label that is at the AHRI test standards at 40 degrees, 42 degrees. That test is useless in cold climates. Get the actual curve from the manufacturer. They're not going to want to share it with you. They're going to give you a bunch of pushback. Give them 5 temperature points, ask them what their capacity is and COP at those 5 points, and build your own curve. You have to design around the equipment. We want to design around mild supply temperatures. I can double my COP if I design around 100 degrees compared to 140 supply water temps. You want to do a cost analysis for adding TES, and especially on the performance side, but make sure you're taking advantage of thermal energy storage for load shifting into beneficial temperature hours, better daytime hours when the temperature is higher. The COP can almost double when we're going from a cold temperature to slightly warmer. So pay attention to it. And then my last plea for all the regulatory folks on board, I'm hoping there's some CEC folks here, consider implementing the Passive House Energy Standard. Even in California, nobody is talking about the benefits to right-sizing a heat pump when your building enclosure is biasing you against heating. Everything in our standard right now is based on TDV and cost effectiveness, but nobody's talking about purchasing the equipment. If I designed the Passive House Building Standard, even in a commercial building, I can almost guarantee you that your heat pump size will be about half of what it is if you follow current code. So that's my plea to the world, is be better designers, be smarter designers, and actually design around real equipment. My last little thing to plug is I promised within the next 2 weeks, ASHRAE will be releasing their Advanced Energy Design Guide. that I helped write 2 years ago. So I'm hoping it's still relevant. I have to go back and check, but it is for every climate zone in the country. We have heat pump. You can't say it is because it's ASHRAE, but it's an all-electric design guide for every climate zone in the country. We recommend no fossil gas systems. Might be an oversight and it's not written anywhere, but there are no fossil gas systems recommended. So it should be out in 2 weeks, and you guys should see some really great strategies you can deploy anywhere in the country. So that's it.
Oh, I was applauding for the last point, but woo! Great presentation, Stet. Yeah,
that's my
the chat is blown up with your applause. So, it's 1:03. Do you need to jump, or can I ask you some questions?
No, I'm happy to answer questions.
Okay, so your last point there about implementing the passive house code, allowing you to reduce the size of the heat pumps by 50%.
Yeah.
And that you studied perhaps the cost effectiveness of these two systems, envelope versus heat.
Yeah, well, I'll tell you. So if you look at, and I wish I had I have a whole slide deck on this, but okay, how long does an envelope, a good envelope, like a good, robust, airtight envelope last? It can last in a commercial building, it can last 50 years. Like if we actually built airtight, tested assemblies, it could have a 50-year lifespan. A good commercial heat pump has like a 15-year lifespan. So if you actually look at the life cycle cost of the investment, the embodied carbon of all the manufacturing of heat pumps and refrigerants, that envelope does a ton of work by doing nothing, by sitting there. It reduces our annual energy use and it reduces the peak. And the trouble with heat pumps is that as an engineer, I have to design for my peak load. If my envelope actually addressed peak load, which none of the code, ASHRAE 90.1 doesn't do it, Title 24 doesn't address peak load. They're just like, oh, that's your peak load. Oh, nothing I could do about it. We absolutely could change peak load. And peak load and outside design air temperature are the two things that are going to kill the decarbonization effort, because we're trying to show a performance. And the heat pumps are sitting here on a design day of 30 degrees or 25 degrees or 20 degrees with a horrible COP. And we're telling people that they're not going to have to pay higher utility rates, but they are. You're going to pay more in December. You'll pay a hell of a lot less in the shoulder months, but you're going to get cream in that peak month. And so a better envelope designed to shift and bias us out of the heating zone into more air conditioning. I know it's a horrible thing to say, but even if you could just shift the entire building performance or the balance point closer to the air conditioning zone, we'll improve our performance, we'll reduce the cost of install, and it's a win-win for everybody.
Implicit in what you're saying is that the winter peak is a worse peak for electrification than the summer peak of air conditioning. Can you expand a little?
Well, because we have heat pumps, that are effective, have really great SEER ratings for summertime performance. There's obviously some grid capacity issues and distribution issues, but we haven't even touched on what those grid capacity issues are going to be if everybody's running at a COP of 1 on design day in the winter when we have no renewables on the grid. And so when I look at the annual CO2 marginal emissions rates, and I look at outside air temperature, all the graphs that we're looking at where they're like, oh, wintertime performance is great. It's not great because the COP is not 3, it's 1.5. And so all those midnight hours, those heating demand hours, we want to shift into daytime so that the heat pumps can actually, be more robust. So it's just taking a little bit of seriousness around the analysis and expanding the dotted line so we actually look at life cycle impact. Envelope, it's all about envelope for up to mid commercial. A hospital, the envelope's not going to do anything. We're moving so much air through hospitals that you might as well have a tent. So it doesn't matter. But for mid-sized office buildings, for residential buildings, I just wish we could get on the bandwagon and climate. Better envelopes will help us put in smaller equipment.
Okay, so I'm clear that at least in San Francisco, you're a mover and shaker with the
I have a very small audience, like 4 people who know I am, so it's fine.
Just blew you up. Everyone knows Stet, one of the most brilliant engineers in our country, doing cold climate solutions, a true intellectual leader. So just so everyone knows, I love it. So are you, I have been resistant towards passive house envelope measures if they were being used in replacement of electrification, saying that the urgency
they're like the best friends. They want to be like, they're like, you know, the best date you've ever had, where you're just like, I can't believe it connected like this. That's a heat pump and a passive house envelope. Like, they're like, oh my God, where have you been my whole life? Because the passive house envelope reduces my heat pump size. And those two things are actually going to reduce our peak. So like, I don't know, like 6 years ago or something, I presented at a conference, and I think it was a passive house national conference that was in Oakland. And I was like, oh, this is so much fun. And a colleague of mine and I presented on the grid benefits of electrification with passive house. And actually we're able to show that you could retrofit an entire neighborhood electrification with no increase on the electrical load by retrofitting envelopes and heat pumps. It's about reducing those peaks. And the passive house envelope lets us load shift. It lets us reduce our peaks. It's heat pumps and passive house are just like, yeah.
All right, I'm hearing you. This is good because I really have been. It's like it's been a tension point because passive house wasn't quite on the all electric bandwagon in the earlier years, but it was.
Oh, they were all like biomass, and you'll burn all this, and I'm like, oh, just pick the heat pump. But
okay, but things have been shifting, so we should be coming back and going out on dates more. I see what you're saying.
Yeah, and for everybody who's like just electrify and ignore insulation, it's ass backwards because the peak. If you've tried to put in a PG&E application to get your meter upsized, good luck.
Have fun.
We're seeing 9-month, year-long delays. Guess how long it gets to get a permit to increase your insulation? It can be over the counter. Oh my God, amazing! And then you can put a small heat pump in your system that doesn't require upgrading your entire panel. If we want to talk about like grid impacts, we have to look at the whole picture. And insulation and thermal energy storage and battery backup. All those things can work together to actually flatten the curve, flatten our demand curve, make it easier to do neighborhood retrofits. Anyway.
Don't be all anyway about this. We're talking about like this is the the important stuff. So
I get really passionate about this. I love heat pumps, but I also like a really good envelope. So
well, let's dig in a little bit deeper. So we met with Saul Griffith, a hero, right? Important person. But Josie, who's going to be speaking next. We met with Saul to say like, hey, your languaging around rewiring everything is kind of unhelpful because it's incredibly expensive to rewire as well as time intensive. We don't have time for that. We need to go faster than rewiring everything. We need to replace out appliances. We need to do load balancing and load sharing. And we need to do a lot of other things besides rewire, which is hard when his organization is named Rewiring America to say the core premise is problematic. So Chris Gilbert here is saying like, this makes me question the Saul Griffith electrify everything point of view, which says to ignore insulating, etc., because it's too expensive. You're contradicting this. How would you respond? Is this specific way to commercial?
I would say so retrofitting existing buildings, like doing passive house retrofits, that's hard. That is a hard thing to do. I'm trying to do it right now at my cabin. That is a hard thing to do for a 100-year-old building. So I'm not gonna fight. I mean, I still think it's a good thing to do, but I'm not going to like throw myself on the sword for it. But for new construction, damn it, we can stop making the buildings worse. Like our new construction should allow us, in my mind, you should be able to get at least 6 hours of load shift out of every new building just through enclosures and being smart and a little bit of thermal energy storage. If every new building had 6 hours of load shift thermally, all of a sudden, from a control standpoint, we don't have to do the batteries. Like there's a ton of thermal inertia in our buildings, and especially small commercial, like 2-story, 3-story commercial that might have, concrete slabs. Oh, there's so much thermal inertia there that we can load shift, and we're not really tapping into it. And so, thermal mass envelope I've done a study where I could move a building. I could stop doing anything to a building for 12 hours. And just let the slab ride with the envelope, regardless of climate zone. With no technology, with a controls package, it's just stop heating and cooling. And so, retrofits are really hard. I'm still a big fan of weatherization programs, but I'm not a fan of just going in and swapping out high load equipment to replace a boiler that was also high load like the UCSF study, even doing the smart things that we're doing, we're going to have to upgrade the panel there because they only have 1,000 amp, 120 panel for an entire facility because they don't have air conditioning and they don't have any loads. Well, now they're going to have loads. We're going to go, taking gas to electric on that project is going to up their loads by 4 times. And that's with doing thermal energy storage and smart stuff. So just going in and throwing in a bunch of massive heat pumps to replace a bunch of gas boilers. Efficiency first. Nobody likes efficiency. It's not sexy. It's hard. Oh, I have to think. Efficiency matters, and it matters a lot for heat pump sizing. So that's all my.
I'm a proud board member of Efficiency First California, which has an exclamation mark in its name, and it's the program administrator for SMUD's electrification program.
Yeah.
It's like, yeah, I gotcha. Because we keep on running into this, like just throwing a technology at it, not.
You're going to end up with oversized heat pumps that are can work for yes, they'll work for that hour you need it, but the rest of the year you don't need it. But your panel had to be sized for it, and you tripled up everything. And then in PG&E's calc, they're like, oh, you got a big piece of equipment. I'm going to charge you a whole bunch to upsize. Oh, I've got to do a whole distribution line. Oh, 4 hours of load shift, and nobody had to upgrade anything. So anyway.
There's so many people's comments. I feel bad like dominating here, so I got to make sure I'm being polite to others. Let's see here. Chris Gilbert goes on and say, yeah, regarding Griffith, of course he's selling a $3,000 smart panel. It's true. I love tech. I love all that stuff, but I'm also I'm out there and I'm just like, you know what I really need is a building that doesn't leak. That'd be a first step, and then I'll size a heat pump. So there's a couple of people here. So Adam Klaus is just commenting that he had wall insulation put in San Francisco, surprisingly affordable. Mm-hmm. Nick Peterson was saying, how does solar PV measure up in the Bay Area versus the cost spent on passive house type envelope upgrades for existing structures?
It totally depends on the age of your home, where you're at. Like, are you in San Francisco's zero lot line where you can't access anything? You've got to rip, you've got to put the holes in your wall and inject and. But I would say that from the retrofit world, and I'll be teaching a course at the Energy Center this April on retrofits. So ZNE DECARB retrofits. So I'm going to go through a phasing. I'll sort of present a phasing plan, at least for commercial buildings. But the idea is that most buildings have a capital improvement budget. So commercial buildings all have some sort of capital regime that they're on, and it's tied back to how much they can depreciate their asset and accelerated depreciation. Like, it's all financial mechanism where everyone's like, I'm making millions of dollars and you get to eat ramen. I'm like, okay, fine. But if you could pair out these improvements on that same schedule in a smart way, so start with glazing improvements, window improvements, and then layering on air tightness, then insulation. By the time you get to that next 15-year mark or that 20-year mark where they need to reposition the asset, they need to depreciate, now you put the heat pump in. And I know that's too late for the, saving the world, but it does mean that I can put much smaller equipment in, and that has ramifications. And so I think there's definitely a world where we want to do everything really fast. And if you're doing a gut remodel of your home, by all means, jump in and do it. My own house in Oakland, it's going to be 100 years old next year. It is uninsulated in the walls. If I pull out a faceplate on the outlet, I can see outside. I'm like, oh, there's daylight. There's no sheathing. We spent all of our money in a seismic retrofit. So, if you want to, there's some insane things that we need to do to up our, but I refuse to oversize my equipment. So we are not transitioning. We've transitioned everything else, but my space heating is not going to go there until we insulate. And it's on our plan. We have to reside the house because that's all, 100 years old, and might as well be a tent. So when we reside, that's a perfect time to re-insulate. It's a very low cost time to re-insulate. But by layering on those retrofit strategies with other improvements, you can get a lot better value. It's really hard to do it. It's like a one-off, unplanned sort of thing. But that's my soapbox.
Good soapbox. And just, other conversations, other presentations about how to more rapidly finance these improvements. Because
the financing, if the financing side can line up with it, it's gold. And actually, the Department of Energy is going to be releasing a guide on layering finance methods and incentive programs. I just reviewed the draft, and it should be out in the next month. But it's a way to for commercial building owners, if you for new construction or retrofits, if you want to layer on 179D tax credit or tax deductions, plus federal incentive programs for renewables and energy efficiency, that we're providing a roadmap on how to layer those incentives to be able to do the most work at once, including depreciation values and recommendations around that. So that should be out in a month, and I can share it with you, Sean. You can spread it to the world.
I'll do my best.
Yeah.
This is let's see here. Oh well, back to solid growth. Chris, like that's something that Griffith is doing good. Suggestions of financing. Yes, it's true. Let's see here. Oh, there's people who are chatting about their homes. Diane Bailey says, Stet, you're brilliant. And I wish you were in charge of designing energy building codes.
Yeah.
But,
oh God, I don't want to do that. I got sucked into that one year and I was like, I don't want to be doing that anymore.
But she goes on to say, but please don't say retrofits are hard. I mean, sure, kinda. Yeah. Retrofits are different from new construction, but entirely doable. See Redwood Energy's guidebooks. Hard equals relocating villages about to be subsumed by the sea. Hard is witnessing towns burning down and erased. On the scale of hard, retrofits are easy.
Yeah, I'll take that. I'll take that as criticism. I would say that from the design perspective, design world, so coming from the engineering, architecture, big commercial projects, owners tend to want to gravitate towards new construction because it's tightly controlled and the unforeseen circumstances are limited. Retrofits present a lot more challenges. So from a financing risk standpoint, owners tend to want to gravitate towards new construction. But I love retrofits. I mean, it's dirty, your hands are in there, and you can find some cool, there's actually a lot of cool stuff that existing buildings have. And I'll give a quick example if there's time. When I was still at Integral Group doing a bunch of work in the South Bay, they did a whole bunch of awesome net zero energy retrofits of these concrete tilt-up buildings, like horrible buildings, repositioned into like hip, cool tech offices, but they're all almost entirely passively cooled with mat ventilation and mass and ceiling fans. Like all that 12-inch tilt-up wall provides actually a ton of thermal load shift. And one of those buildings installed air conditioning and it never turned on. Ceiling fans plus mat vent doing a night flush cycle made the buildings not need air conditioning. So instead of just throwing on heat pumps onto these existing buildings because we're like, well, I saw the furnace size, I saw the air conditioner size, take a step back. And if you do a good retrofit with good insulation, you might not need air conditioning. And all that embodied carbon is already there. Take advantage of it. If the concrete's there, it's mass. It can work for us rather than putting new embodied carbon in a bunch of more equipment. So there's a bunch of great companies doing amazing work. And yeah, it's just hard because it's not, it takes thought, it takes time to do that as opposed to new construction, which people just stamp out, unfortunately.
Susan Gladwin had a question on this. She says, sorry if you covered this, but how do you manage thermal storage that's coming from the cement slab or other structural things for demand response?
So it starts with trending. So so we write our own control sequences, and we just got another patent for an AI sort of based trending system. But essentially, you can test your building's thermal response by changing its temperature, like even on the weekend when no one's there, or start testing it while people are there, and they actually probably won't notice because not that much changes. But you can trend a building in different seasons and look at what its thermal response is relative to outside air temperature, relative to inputs from the HVAC system. And you can actually get a sense of how long your building can quote unquote float before you need to interject cooling or heating into it. And there's actually a really great paper that was written by Susan Ubalodi, George Loisis, Brendan Levitt at Loisis Ubalodi. They're in Alameda. But the paper is called Thermal Autonomy. And it's a research paper that talks about how to design buildings that essentially can let you float. It's like daylight autonomy, where if the power goes out, you have enough daylight to work. Well, it's the same thing with thermal autonomy. If the power goes out, how long can you float before people actually would have to leave your building? And it's actually surprisingly long. If you actually start to do the energy modeling, you can get a building to float several hours before you actually need to do something to it. And the more mass there is that's exposed, the longer that is. And if you want to go crazy, do a heavy mass radiant slab. And man, you can get almost 24 hours of load shift out of a radiant slab that you can pre-inject the day before. There's a whole bunch of fun stuff you can do. It's all in the controls. And you can, yeah.
Is this the paper you're referring to?
It is, yeah.
Excellent.
I highly encourage people to read it. It sort of sets a tone. It's a different kind. Instead of HVAC being there right at the moment to make everything exactly the same, it's embracing a little bit of temperature float, and you can get a ton of demand response out of thermally autonomous building.
Let's see here. I think Kathy Nicholson, one of your peers, she said, efficiency always matters, but it should be done in parallel, i.e. at the same time as with electrification.
Yep.
We don't need to reduce before we produce. We should compromise to optimize. She's got her jargon.
If you can afford to do them at the exact same time, obviously do it at the same time. But I just don't like putting in stuff that's too big and then retrofitting later and then being like, because then I'll warn you, if you put in something too big once, every 15 years, somebody's going to put something in too big. Nobody does the analysis when they do they look at a nameplate and they're like, well, that was 6 tons. I guess I need 6 tons. Nobody complained. 6 tons it is. So in perpetuity for the rest of that building's life, it's going to have a 30-ton chiller because nobody is going to take the time to care. So don't put stuff in too big because you're setting it up for a lifetime of being wasteful.
Brutal.
Yeah.
Brutally true. There's not enough people who are really working hard on these things, sadly. I want to make sure I'm getting other good questions here. Let's see. Well, there's just so many comments, it's hard to even get through them all. But so Chicago.
Yeah.
So you are, like you went over and you checked out the new big central heat pump water heater. That's the CO2 one. The name is escaping me. It's like you flew out to the factory.
Link, the one from Link. Yep. Yeah, I flew out to their factory in New York just a couple months ago, and it's really nice. I mean, I would eat breakfast off of that heat pump. It was so nice. And why I'm getting so excited about it is, one, global warming potential of the refrigerant is not even a concern, but also it has very high temperature performance at a very low ambient outside with a pretty decent COP. And so when you combine those two things, it just gives me a ton of flexibility as a design engineer to pair that with thermal storage and do some really fun stuff. They have a water source unit and an air source unit. The air source unit has an optional, as I mentioned, heat exchanger where you can actually do heat recovery off of the chilled water return. So that's our basis of design on a couple projects right now that we're moving forward. And I'm flying out, or I'm leaving in a couple hours to go probably catch COVID at ASHRAE, but I'm going to Las Vegas, and so I'll be reporting back on any good heat pumps that I see at the AHRI trade show. But I'm hearing a bunch of chatter about some new CO2 products and some also, is it Samsung? I forget which brand, but one of the VRF companies is launching in Europe their CO2 VRF, which would be a game changer. And I don't know how they've gotten around the simultaneous heating and cooling snafu of CO2, but they said they did, and they promised to give me a walkthrough of the product.
And they're going to run refrigerant around a building with CO2? Well, how do they pressurize and seal that?
I don't know. That's like, I have a whole list of questions from them. They sent me a thing and they're like, can't wait. And I'm like, are you coming to the US? They're like, oh no. And I'm like, of course not. But anyway, they say they're working on it. So I have no idea how they're going to trace a leak on that if it starts leaking, which is why I hate VRF, but that's a side story.
No, I've been really excited about how mini splits are getting up to now 8 heads, and they're getting to be bigger. Like you can get a 6-ton mini split that has all the internal manifold, internal pumps and things, and it comes packaged as opposed to having to, so you can plug in. Yeah, it's just like sending big tubes of refrigerant to manifolds and to pumps is so expensive. Holy smokes, it is the most expensive way of all the ways to do HVAC. We've done all the value engineering, cost benefit analyses and bidding, and It's just like, damn, it's like $23,000 an apartment versus 15 or 7, or, it's like, whoa, not cost effective. I mean, just blow you out of the water expensive. I think Kurt Hurley, you can take the last moment here, and then we're going to transition over to Josie. And thank you so much for entertaining us during our lunch hour. Kurt says, there's another building thermal autonomy metric known as TOW, which was introduced by Graham Irwin. I have advocated for it with PHCA as an alternative metric to TDV to correctly value grid support of passive house, peak load shaving, and load shifting. Have you any response to that?
That would be amazing. So I would love for the Energy Commission to recognize the grid benefits of any design solution, and not just TDV, but in my mind, if we could get building standards to get to the point where every building, as I mentioned earlier, had some time-dependent load shift capacity, and it was up to the designer, the team, or whomever to figure out what that was. I would love to see the standard recognize that and actually provide a benefit, like a compliance benefit for doing that. So whether it's TOW from passive house, whether it's 4 hours, 6 hours of load shift, or a percentage of your total load that's shiftable by 4 hours, that would be very exciting. I would back that 100%, because grid optimal or grid friendly design is where every building needs to go for new construction, or else we're in 10 years, we're going to be kicking ourselves because we're going to have a bunch of spiky loads, and it's going to be really ugly on the grid. So.
All right. Thank you, Stet.
Yeah. Thanks, everybody.
Stet. Brilliant. So much appreciate it.